in these additional notes, we will review some of the strategies we've already learned and learn some new strategies. And that's where this starts to get trickier, because the more strategies you have, the more options you have when you read a problem, and every problem will be its own word problem that you have to sort of decipher what kind of question is this. Now, this is part of a branch of mathematics called combinatorics. If you're in university and you see a combinatorics class in the math department, you'll know it's all about counting. And counting sometimes is easy and sometimes gets complicated. Right? We've already been like, if I had started this unit with like, can you rearrange the word Mississippi in as many ways as possible? It would take you a long time, right? But we learned today how to deal with that, how to use factorials to figure that out. So the very first thing we did was the fundamental counting principle, right? This is where you make a space for every decision. If you can, underneath the space, describe what you're deciding. I need to decide on color, I need to decide on transmission, and I need to decide on the interior. Then write down how many choices you have for each decision, 3 choices, then 2 choices, then 2 choices. We multiply, and you would get 12 ways in total of choosing this car, right? This could be problematic because if you think right now, how many options are there when you buy a new car? So many options. So you don't want to be like, you don't want to like have a new hobby, and your new hobby is that you collect Honda CR-Vs from 2023. I've got every color, every different model. You know how many cars you'd have to buy if you wanted every single option for the 2023 CR-V? I think it would be quite a few. It'd be a very expensive hobby. Plus, I don't know where you would store them in your room. So. How many 3-digit numbers using the digits 1, 2, 3, 4, 5, 6, 7? Again, this is the spaces. You have decisions. What number you're going to put first, what number you're going to put second. And now we're getting into this a little bit more of a description. One of them says you are not allowed to repeat numbers. The other one says you are. Well, if you're allowed to repeat numbers, let's do that one first. There would be 7 choices for your first number. And then you'd have 7 choices again, because you could use any of those numbers again. And 7 choices again for 343. But if you were not allowed to repeat the numbers, like this was just a list, and once you pick up the 5, it's gone, do you still see that you would have 7 choices for your first one? And then, one of those numbers is gone. Now we have only 6 choices, and then 5 choices. And we learned that this could be written as 7p3, 3 spaces starting with the number 7. And if you multiply this out, you'll get 210. And now we're ready to learn a new strategy. The new strategy is in this next question. We're still going to use the numbers 1 to 7. And we're going to ask how many of those 3-digit numbers using 1 to 7, not repeated, are even. So it's still a spaces question. Just because. I'm going to use 1 to 7 for the next question too. You'll see the just because after as the reason. So this one has to be even. And before, the strategy is listed there. It says you deal with the restriction first. But I'm going to show you why you need to deal with the restriction. Don't write this down. I'm going to switch to red pen because I'm going to make a mistake. But I'm going to make a mistake how most people logically think about this. Most people, when they have decisions to make, they make the first decision first. So they would say, well, how many numbers could be the first number? Well, all 7 of them could be the first number. And now I've used up one number. How many choices do I have for the second one? 6. And then I've used up 2 numbers. Now, the last one has to be even. If we look here, do you see the 2 is even, the 4 is even, and the 6 is even? Okay? So some people will do this and it's wrong. Why is the 3 wrong there?
Because you could have used any of those numbers already.
Maybe the 2 is gone. I don't know which number it is, but it could be the 2 is gone, or maybe the 2 and the 4 are gone. Or maybe they're not gone. So this should be 3 or 2 or 1, I don't know. Right? And the math, if you do, I don't know, this is not a good answer. That doesn't work. You can't just multiply with the I don't know in there and get a final answer. We've got a problem. So what we do instead is we say, let's deal with this restriction first. Right? The even numbers are 2, 4, and 6. If you make that decision first, I'm going to pick one of those numbers to be my last number. I have 3 choices. Now the 2, the 4, or the 6 is gone. How many choices do I now have for my first number? 6 are left, and then 5. Multiply this together, and we get 90 ways in total. This is a new strategy of how do we count when there's a restriction. Label the restriction and do that first. Because we guaranteed, by doing this first, we guaranteed our last number was either a 2 or 4 or 6. Can you see that if you pick the 4, it's still possible to have a 2 out front? If you pick the 4, it's still possible to have a 6 out front. And if you pick, I don't know which number I haven't set, you pick the other one, it's still possible to have the other one in front. So we deal with our restriction first, make sure we get what we want, and then we can deal with our other decisions afterwards. So again, I want you using 1 to 7. I want you to solve this one using the strategy we just learned. 3 spaces, here's our restriction, this is odd. And then once you get your answer, I want you to see how you could use example 2 and example 3 to get the same answer in a different way. Because that will introduce to us another strategy we can use. So first get it the way that we just learned. Your choices here are 1, 3, 5, and 7. Now you would have 4 choices. You've used up a number, then 6, then 5. Did you get 120? And can you see how you can use the results that you got in question 2 and question 3 to get the same thing? And this is going to introduce to you a very important strategy that I call the NOT strategy. And the NOT strategy works like this. If you want to count something that's not something else, first you count all the possibilities. And you see that we did that in example 2 and found out that there's 210 with no restrictions. Then you say, I already counted all the bad ones. Can you say of those 210 ones, the even ones are bad? Those aren't the ones we want to count. So if we subtract the even ones, which we got to be 90, the ones that would be left would all be odd. Now in this question, strategy number 1, I think, is still the easiest. It's easy to count with doing the restriction first and then dealing with the other stuff. Works perfectly. There will be some questions where counting something directly is hard, and the NOT strategy, counting the bad ones, will be easier. And when you're counting the bad ones, then you subtract them from all, And what you're left with is the good ones. So that's called, in my world, the not strategy. That is strategy number 4 that we've learned. Right? We've learned the spaces.
But it's not a strategy.
It is a strategy. We've learned dealing with the restriction. We just learned the not strategy. And we also have the identical objects, which we'll review in this note package as well. All right, I want you to try this one on your own. 3-digit number, using 0 to 9. You're not allowed to repeat. How many choices do you have? And I'm looking for common mistakes. Oh, you guys are so good. You're making the common mistake. Makes me happy. All right. So, some common mistakes. It is not 987. That's a common mistake. Another common mistake. It is not 1098. It's not 987 and it's not 1098. Okay? And the reason is that there's a tiny restriction in this question. Can you see the tiny restriction? Is this a 3-digit number, 34? No. That's a 2-digit number. We have to be careful in these questions because if this question had codes, right? If I needed to get into your iPhone, I can start by putting a 0. That could possibly be your password, right? But as a number, you can't start with a 0. This is not a 3-digit number. That's a 2-digit number. So we have a restriction that this is not 0. Dealing with that restriction first, you see there's 9 choices for that. Now how many choices do you have for the second one? It's not 8, because 0 got put back in, but one number is gone. 9 choices left. Now you've used up 2 of the 10 numbers, 8 choices for the last one. For 648. So these questions you have to read carefully because like I said, if this said codes, then it would be 1098. Since it said numbers, we have a restriction, this isn't a 3-digit number, then it's 998. These will all be mental math questions. With our factorial notation, you simplify factorials. You can only get rid of factorials if you have the same factorial on the top and the bottom. It is never allowed just to be like, ooh, exclamation mark over exclamation mark, I'll make them go away. No, that's not allowed. The only way you can get rid of an exclamation mark is with the same number on the top of your fraction and the bottom of the fraction. So the way that we go about doing this is we expand the bigger one, 7, then 6, and then when you get to 5, you say, well, it would keep on going, so I can write 5 factorial. That 5 factorial matches up perfectly with this 5 factorial. Then you can simplify, and you would get 42 on bottom. Same thing in B. The biggest number is the 10. You can only get rid of factorials if they're identical, so I keep going until I get to that 6 factorial because I had a 6 factorial on the bottom. Those will simplify. But I also have a 4 factorial, which would expand all the way down to 4 times 3 times 2 times 1. Mental math, would you agree that 4 times 2 is 8, and that would simplify with that 8? I'm switching colors here so we can see what canceled with what. Otherwise, sometimes canceling stuff, if you're all just using pencil, it looks like a massacre happened and then you somehow come up with a number. And if that number is the wrong number, then I have to like look at your massacre and try to figure out what you did. Nine and 3 aren't the same, but 9 divided by 3, it leaves you with 3. Does that make sense? In purple? So now what am I left with? The bottom is just 1. And on the top I have 10, a 3, and a 7. 3 times 7 is 21 times 10. 210. When you get to variables, it's the same idea. But sometimes it's a little hard to see which one's bigger. Okay, n plus 2 or n, which one's bigger? N plus 2. So if we expanded our bigger one, what's 1 less than n plus 2? N plus 1. What's 1 less than n plus 1? N. And when I get to n, I'm like, woohoo! Can cancel those out. And I'm just left with n plus 2 and n plus 1. Where I find students get into trouble with expanding the bigger one is if I would do something like this. Let's do this one. Okay? Problem is your gut. Your gut sees a 7 and sees a 5. And which number does your gut think is bigger when it sees a 7 and a 5? You've got a weird gut. Right? Can you see that you probably normally like see the 7 and be thinking bigger just because it's a bigger number, but with the subtract sign, the n minus 5 is actually bigger. Plug in a number like 10. 10 minus 7, that's 3. 10 minus 5 is bigger than 3. So, when expanding the bigger one, you would expand the bottom here. So we leave the top as n minus 7 factorial. We would have n minus 5. What's 1 less than n minus 5? n minus 6. What's 1 less than that? n minus 7. And sure enough, those would cancel out. Careful. You would have 1 over n minus 5, n minus 6. What is left is in your denominator. It stays in your denominator when simplified. I should create a question that links these two units. How could I do that creatively? Get you to do something like graph y equals 1 over xp2. And then you'd have to use the formula and simplify it, and then you would get a rational equation with asymptotes and have to solve it. Good idea. Okay, we won't do that right. Now, when you have a set of objects that you're arranging in a specific order, we call that a permutation. We've seen this already. Like A, B, C could also be A, C, D. You could start with B. Then you could have B, C, A, and you could start with the C. And we counted permutations in the same strategy as the spaces. How many choices for the first letter? 3 choices, A, B, or C. We've used up something, then 2, then 1. And this is where we really use our factorial notation a fair bit. And we have our permutations formula. But interestingly, this note, if I did like 5p5, remember how the second number is the spaces? So 5 spaces, and the first one's the number you start with, so we go 5, then 4, then 3, then 2, then 1. Which is obvious to be 5 factorial. But in the formula you get a 0 factorial. When we had in our textbook, that 0 factorial doesn't make sense according to the normal definition. It has its own specific definition that it has to equal 1 in order for the formula to work in certain situations, and this is one of those situations. With the spaces, it makes total sense that it's 5 factorial. But in the formula, we get a 0 factorial on the bottom, and we're like, this doesn't seem quite right. What should we do with it? Well, it has to equal 1. I don't think the school has a wind ensemble anymore. We'll just say, oh, this would have been way quicker to type. I don't know what I was thinking. Band.
You held too much respect for the wind ensemble.
Yeah. Does the order matter? Yes. Most likely, they probably were forced to learn O Canada, and if you're at a school concert and they play O Canada third, it's awkward. It's just kind of like, oh, maybe you should do it at the end, and then say thanks for the standing ovation.
No, they play O Canada first, and then they do their program.
That's what usually happens. That's what I'm saying. The order does seem to matter.
What's a wind ensemble?
That's when just wind instruments. Nobody who bangs things is allowed to join.
Just blow off the wind.
No percussionists. What else was not allowed? Strings, right? They're too uppity anyways, right? So this wind ensemble's like, no.
Wind ensemble just
Contribution
I'm tired of the violinist who's always telling us what to do. They're not allowed. This is
no pianist.
So this would be one that I would say, solve with spaces. You have 4 decisions. What song are you going to pick first? You have any of the 10 choices. Okay? It is a concert. I hate going to those concerts where it's a 2-hour concert and they play the same song over and over again for 2 hours. Probably going to choose a different song, then 9, then 8, then 7. This would be the same as 10P4. And there's a lot of different programs that could be made. Yeah, well, Canada at the end, guaranteed standing ovation, no matter how bad your band is. Although we have pretty good bands.
Unless you play with the Paralympics.
I guess so. Number of permutations of the word map. Order matters. Does it make sense? This would just be 4 factorial. All the letters are different. No problems there.